welcome back to the studio stage. Our next talk is Boost Your Search with Embracing Vector Search. And the interesting thing is, I tried to talk to the presenters beforehand to have something to talk about, to introduce them on stage. And in this special case, it's kind of funny because I'm sure Tobias could say a whole lot about Alexander being one of his colleagues or one of the other many Sandstorm colleagues here in the audience, but I'm the one introducing him and I have no clue. So I talked to Alexander earlier and he said there's absolutely nothing interesting about him to, to introduce him with, which I think is a blatant lie. I know for sure that Alexander is an amazing developer and part of the tech team here for the conference. So that is enough for me to be very happy to have him on stage. Come up here. Thanks and welcome, Alexander.
Thank you. Thank you. I was not aware that this was already the interview for my introduction. Okay. Hi, thanks for having me today. I'm Alex. I'm one of the full-stack software developers at Sandstorm. I'm mainly focused on back-end development and everything infrastructure, and I want to talk about vector search today. That worked really great. Nice. Okay, so I want to talk about what vector search is, what it does, how it works, which problems it might solve, and which problems it will not solve, or even which problems it will introduce itself. So before we can talk about vector search, we have to talk about search in general. So let's start there. What is a search? Well, most of the time you go to a website and there's the little input field and you type in the thing you are looking for, you hit enter, and your visitors expect your page to show you a list of things that matched your search term. And especially for online shops, this is one of the most interaction points for your customers. For example, when you go to Amazon, has anybody ever used those menus or categories, sub-navigations? I did not even realize they were there till the screenshot. So most of us do, we head straight to the search bar, we enter the name of the thing we want, or maybe we do not even know what the thing is called, we hit enter and Amazon will figure it out for us. It's a really great search, even if you don't know what you're searching for. When you got some strange tool or part you're working with, and sometimes you basically do not know what it's called. And I personally use the Amazon search to figure out what it is, what I'm actually searching for. And Amazon will most of the time figure it out and give me the list of products, I can buy them. I finally learn what this thing is called, and I can buy it on Amazon or a more nicer online shop or even in my local shop. So the main problem I have with this Amazon search is it's really, really good. And it is that good that most of our customers or potential customers for online shops, they are used to that quality of search, especially when you compare it maybe even with Google. Google is that confident in correcting your errors. It will just give you a little notice like, yeah, you mistyped it, but here are the real results you're looking for. So that's search. And like I said, in contrast to Amazon search, for me, when I have the task to implement search, it's mostly, oh, okay, I will just install a simple search or some other pre-built package, throw it in, add some styling, maybe some styling, and call it a day. So this implementation I will reference as traditional search. That's the naive implementation of I need some kind of search. For when you go like, yeah, search, we just add a package and call it a day. And the thinking behind that traditional search is, well, we got a database, we got a table, we got the contents, well, just search in that database, like maybe this, little abstract, but yeah, that's search. You search all your data and you call it a day. So, does not work that great with the pointer. Okay, so your search is done. Yeah, you commit it, you push it, you deploy it, and maybe you even go live with this search implementation. I hope you don't go live with this implementation. Because as soon as somebody starts to use your search, you're getting really into problems. Well, you might ask why this is a problem. Well, first of all, when you got a DevOps team, they will probably call you really, really fast because the like operation in this query is not indexable. What happens as soon as you got a couple of thousands or tens of thousands of contents, every time you search, everything is searched with this like operation, and your database will maybe hold up, but at least your CPU will not be happy. And it's like having your own denial of service attack built into your site. Not that great. And worst of all, you go through all the pain and the results are maybe mixed. So yeah, not that good. So you get a task assigned to improve your search. And you do a little research and you start to come across something called the full text index. Nice. So what the name says is, well, it's an index, it's a database index for your full text. So basically you get the same thing as before, but with index. And this is basically available in all the larger database engines. And looks something like this. It's not that different. Instead of a like operation, you get this nice match syntax against your table, against the column you're searching with your search term. And there are even some modes that will handle some kind, I think in Postgres even some kind of stemming, or there's a little bit of magic inside, even reducing filler words and stuff. But it's definitely one really big improvement for your search. So again, you commit it, you push it, you deploy it. Toby, can you put the antenna somewhere else? Okay, so your search, you're finally done. The clicker's really great. Okay, Toby, can you hit, thanks. All for that sweet animation. Okay, so you basically have improved your search quite a lot. Your DevOps team is ready, and then maybe your QA department comes around and tries to search your search, and your search is not that great anymore because they do a very, very nasty thing with your search. They try to use it in German. And the German language is really, really not designed to be searchable or operable by machines in any way. So first, small, really easy fixable problem, but it's a problem you have to keep in mind, is we got those nice Umlaute. And technically, your Umlaute are different letters. And when you do not take care of it, when you search in your German database for Apfel, which means apple, you will not find your Äpfel, which are apples, just a plural, but they will not find each other. Depending on what your customer searches and what you got stored in the database, potentially you don't get any results because you used an umlaut or not. Easy fixable, but you have to keep it in mind. But your full text index will stumble across even worse things. We got compound words or compound nouns, or in general compound words. Everybody not German? In Germany, we got this nice little feature in our language where we can combine any arbitrary number of words together to create endlessly long, massive words that we can use instead of a single sentence to describe one thing very, very, very specially. So it gets really, really abstract. But to make my point, I will just choose a small sample. We got in Germany, we got Frischkäse, which translates to cream cheese. This does not sound like a problem yet. Well, like I said, Frischkäse consists of two words, the words frisch and the word Käse, fresh cheese. Well, Still no problem? Well, your database, your full text index, will not find your Frischkäse when you're searching for Käse, because in most database engines, you're only got a prefix search and not suffix search, or even in the middle search. What that means is, when you're searching for Käse and your word starts with Käse, everything works fine, but as soon as the word cheese, Käse, is at the end of the word, there are no hits. You will not find your Käse. And how our language is structured, the most general word is at the end. So when you most likely are searching for a later part in the word, and your full text index will simply not find it. So another shortcoming of your full text index, the list is quite long, to be honest, you will not find your typos. As soon as somebody is entering something the wrong way, it happens. So maybe you just mix up some letters, or you straight up do not know how to write that word. For example, I'm going to look for cappuccino, and why I'm not getting any results. Well, we can try it again. Maybe I mistyped it, and I still don't get any results. And third time's a charm. This is actually how you write cappuccino. I was sure there was an H in it, but it's not. And to be honest, most of your customers will not try to search 3 or 4 times before getting any results. They will just straight up leave, or try it they will not try it 3 or 4 times. And well, they are used to your search to be that good to compensate for that. And well, that's near like the end of your full text index. That's how it slowly starts to disappear. It's still great, it solves many problems, and you can fix all of those issues with different patches and patches and patches, but you will not fundamentally fix your full text index and how we implemented search so far. So, well, how do we continue? What if we could reimagine how search works? Currently, we are just looking for letters. We are searching for single letters we entered, and we take our letters, put them into our database, and searching for exact letters. But this is not how we humans work. We as humans, when we think about cappuccino, it's not the spelling that comes into mind. When we think about cappuccino, it's more like we think about coffee. It's espresso with latte, and those are a couple of words that come in mind. We think about the semantics, about the meaning of that word. We do not think about letters, at least I don't think in letters. And when we got this cloud of words, we imagine we could just plot all of those words we all have in our language, plot it in a 2-dimensional space, and maybe you got your coffee world in blue and your PC parts in red and, don't know, bike parts, whatever there is, and you just can plot it. And as soon as somebody comes on your site and says, I'm looking for cappuccino, and instead of searching for those letters, we could just say, okay, well, that's coffee, that's our coffee world. This right there, this is cappuccino. And when you're searching for cappuccino, well, if we can throw a circle around it and can say, okay, well, that's everything cappuccino. This is the most semantic, important things you want to have in your search results. So, welcome to my talk about vector search. We can now finally talk about vector search, because this is basically what vector search does, or at least what I want vector search to do. So, how do we continue from here? It's the year 2026. We have to use AI. There's no way around it. Well, we have to solve our problems with AI. But we don't have to use it, but this is the strong point of AI implementations we have. What AI really is great about, what it really is strong in, is natural language processing. So the process of converting our human language, what we say, what we mean, and converting it in some kind of mathematical model. So those words you enter, or your text, your documents, your books, everything in your database or on your site, we want that to be converted in some kind of mathematical thing that the computer can work with. And that thing is called an embedding. An embedding is basically a numerical representation of meaning, really, really abstract, I know, but it's basically transforming anything you give it, like words, document, probably also have seen a conversion of images or the code you write, and we want to convert it into vectors, a giant list of numbers, and that list of numbers we can then give the computer and say, okay, now find me something that is close to it, like give me a number that's close to 7. Well, that's doable by a computer. And the embeddings, those giant vectors, well, they are really, really large. We typically are talking about, it really depends on, on what you're doing, but they are starting from 300 dimensions up to thousands of different dimensions. And the more dimensions your embedding has, your vector, the more meaning you can store in that embedding, in those vectors, but the larger they get, and it's harder to compute, but you basically get the point. And that processing of generating those embeddings is basically plotting everything in a n-dimensional space. This is 2-dimensional. Your computer will probably use thousands of dimensions or hundreds of dimensions to sort everything into those meanings, in those chunks of meanings. So, nice. But how do I get those embeddings? Well, you probably have some kind of account or subscription or anything to already generate those embeddings. You can use it locally with Olama, you can use Mistral, you can use Anthropic with Cloud or OpenAI. There are plenty of API solutions or on your local machine things. You can even train your own embedding model, basically, if you have time for it and the know-how and the hardware. But there are really, really easy entry. There's a really easy entry to those APIs, and you can basically embrace them. You don't have to do the hard work. And creating those embeddings is the hard work behind vector search. The rest is basically just implemented. So how do we implement it? Well, first of all, we have to create all the embeddings. Basically, we have to build up our search index, and what we do is, well, we got our database. We extract all the contents, we do it iteratively, so we get maybe one of our NEOS documents as input, we send it to the API, maybe you got your local Olama running with some Qwen3 model, or you send it to Mistral, and you get your document, and it's converted into this nice vector, into this embedding. And then we got an embedding. Great. But to really build up some kind of search index, you have to store it. You have to store your embedding anywhere. But you have to store it in some kind of vector database. And this was the part where I struggled most when trying to implement vector search the first time, because I started to research and ended up in some giant open source libraries with page-long documentation on how to run it, Docker containers without any documentation, payments I have to do, registrations, please contact our sales, forms, which we all love. And luckily, I found something very interesting, and I hope you like it too, because you basically do not have to do anything to store your embeddings. I bet most of your projects using NEOS already can store your embeddings because, well, all of those 3 database engines already support everything. They got, maybe you have to upgrade your database, because we used to run MariaDB in version 10.11, I think, and vectors are only supported since version 11.6, but I never had any problems upgrading my database engine anyways, so just upgrade to the latest version and you get everything you need to build a vector search into your project. So the nice part is we got our embedding and we just can put it back into our database and call it a day. This is how we create our search index. So what we have done so far to implement the vector search is we got our database, we got the content, we send it to, for example, Mistral. Mistral gives us the embedding, the vector, and we store it back. That's the first part of search. That's building a search index. The second part we have to do is, now somebody actually wants to search on our site, and what we do is, well, we do the same thing. We send a search request, the search term, we send it to Mistral. Mistral sends us the embedding, the vector, and what we can do, well, we compare the vector against the thing we already have in the database. And all of those three database engines, they already support vector search natively in SQL. So, well, that's basically implementation of vector search. I know it's a little bit underwhelming because it's quite complicated what you're building up, and the actual implementation is quite easy, but that's the charm of it, because you don't have to build up giant, complicated infrastructure around everything. It's a really nice solution, I think. At least I like it. So what we have implemented here is exactly that red circle around all of our search content, around all our content, which matches our the thing we wanted to search. Well, let's write some code. It's, as I said, not that complicated. All we do is basically we create a new table, we link it with maybe our content. It's simplified SQL, don't look too close at it. And then in our content embeddings table, we create another column to store our vectors in it. That's what this vector data type actually does. And you have to supply how large your vector will be. The disadvantage of this approach is basically when you switch your embedding model. For Mistral, for example, Mistral embedding model will always return an embedding with 1024 dimensions. When you're using Olama with Qwen or something, you can freely choose how large your embeddings should be, but every time you change that, or even when you change the embedding service you're using, you have to remove all your embeddings, maybe even delete the embedding column, create it new, and based on that you have to create a new index. Yeah, so for your database to actually create the vector results, to do the actual search, we have to create an vector index. Don't be confused, at least IntelliJ does not support the vector syntax and function names right now. It basically just says you, no, I cannot do this, but it works. And what we do here is create another index like any other index with two arguments. We got this m operation, this m parameter, which tells MariaDB, MySQL, how the index should work. And you can tweak those numbers a little bit, but to tweak it, you have to understand what it actually does. Well, the vector index is basically just a giant graph you create. You're interconnecting all your embeddings together, like imagine it being plotted into two-dimensional space. You basically connect the dots. And the m parameter just tells your database how much connections you want for your embeddings. And this is really helpful for your database to perform efficient search. It avoids the problem of going through all your embeddings you have created for your millions of contents. You basically just pick one that's close enough, and then you look around which contents, which vectors are nearby. And you then can choose your m parameter. Lower m means less connections. It's faster to insert, but your results may not be that great, or you can increase your m parameter, means more connections inside your embedding graph. And you can play around with it. I found out that M being 24, so 24 connections per embedding is a nice sweet spot. When you got time, you can start to play around with it, but basically I found out 24 works nice and called it a day. So the next point is the distance. So which operations actually used to calculate the distance or store the distance between different embeddings. And there's Euclidean, and there are a couple of difference, but using cosine, basically you tell your database, search on how similar your embeddings are. You can also use Euclidean distance, which means it really calculates how close all dots are. But also I figured out that actually searching for the distance of those embeddings is not really efficient, not really good. You want to find things that are similar, not close to each other. So the similar the vector is, the direction the vector points, the closer the results are and the better your search results get. So that's your search index built up, and then you just have to use the search index. There's this nice vector distance cosine function which you can use. You tell your database where your embeddings are stored. You tell your database which embedding you are searching against. Then you join your contents together and, well, we build a vector search. Nice. Sounds way too easy. Does it actually work? Yes, it does. So I tried it at our Sandstorm website. Don't ask why I searched for Klemmbausteine. It's the genre category of Legos. I have no clue where that came from up. But before implementing vector search, there were no results. As I expected, we usually don't play around with Legos. Okay, sometimes we play around with Legos in the office. After implementing the vector search, well, I found a nice blog post about the Lego League in Dresden. Klemmbausteine is the genre of toys that Legos are, and Klemmbausteine, Legos, they are really close to each other, so our search find the Lego League. Nice, it works, it's working. Another test was our Klima app. It's an app for your local community, and you get challenges. Yeah, it's a nice app. You can try it at least when you're in Dresden. But the real big problem of this app is, I think, is the name. It's when you say somebody, yeah, just download the Klima app. Nobody knows how to spell it. And before implementing vector search, there were no results. People started to come up with different writings, but magically AI, vector search, it solved our problem. Finally, Klima app comes up in really brutal writings of this name, and you get your results. Nice. Then we tried it in our Ökokisten. People frequently attending the NEOS conference maybe have heard of our Ökokisten project. It's basically some large white label solution for your farmer shop, or at least it's a giant shop where you can shop for groceries. And before implementing vector search, well, when somebody searched for cheese from France, Käse aus Frankreich, there were no results because nobody calls it Käse aus Frankreich. And after implementing the vector search, well, we finally get some results. So the people no longer need to search for Comté AOP 45% fat. They can search by the thing they want and not by the name they expect it to have. Also, when people try to write Gorgonzola, it's from our Matomo statistics. It's one of those words that get often misspelled. We finally can find Gorgonzola. Nice. So you might now ask, well, why are we not just simply using Elasticsearch? And it is a really good alternative, but to be completely honest, I have no clue how to use Elasticsearch. And when we look at some basic project from us, well, we got our web server, that's Caddy. You have to know how to configure Caddy. We get our Neos, that's PHP. You have to combine Caddy and PHP. You have to know the Flow framework. You have to know Fusion. Then there's Redis, that's a database using SQL. Then you have got your SATS watcher, that's another language you have to be aware of. And then you also got Elasticsearch. It's quite overwhelming, and especially Elasticsearch comes with its own language. You have to think about how your data gets into Elasticsearch. You have to think about your data getting out of Elasticsearch. You have to think about your data not getting stale in Elasticsearch. Yeah, it's really much. It's a lot of mental load that's created with when you try to use Elasticsearch. I do believe Elasticsearch is a great solution for many projects, when you know how to use Elasticsearch and you're willing to pay that increase in complexity. Well, yeah. So how does it perform? Well, now the performance in numbers, well, for the first thing I did is calculate a bunch of embeddings. From our Ökokisten shop, I extracted 100 products and tried to create embeddings on my machine using Olama with Qwen 3 on my M1 Max laptop, that's somewhere around there, and creating 100 embeddings in a single batch on my Mac was basically unusable. It took, especially when the caches were cold, it took like 5 minutes just to create 100 embeddings, which is ridiculously slow and not usable for production. Then I found a blog post telling me, well, don't ever try to use Mac OS and Olama using a Docker container, because all the nice performance improvements that come with your GPU, with your natural processing unit on your machine, that are all gone using Docker. Use it natively, and 10 seconds, over 3 minutes, that's a nice improvement. We also used another MacBook testing those 100 embeddings. We used some old server we had lying around from Hesse, and we used a newer production server from us, which we happened to send around. And well, 32 seconds to create 100 embeddings, and you have to keep in mind that every time somebody uses the search on your site, you have to create one embedding for this search request. And when we talk about 32 seconds for 100 embeddings, it's okay-ish to have that kind of numbers waiting for a search. But then I used the Mistral API and OpenAI and Anthropic, and creating those 100 embeddings just took less than 1 second. And this is with the whole TCP connection building up, sending the request, then processing it, and getting it back. This is the reason why we currently choose to use Mistral for our projects. And it's even not that expensive. I have looked it up earlier. You're paying like 10 US cents per 1 million tokens. It's really cheap. We indexed the whole Ökokisten, one of those shops, and it's, I think, point something of a cent, which we had to pay to Mistral to create those indexes. The trade-offs, especially in performance, were not worth it to host it locally. But we will keep it in mind that you can host it locally when privacy is a concern, or you basically just want to use it locally. Okay, nice. So we now know some strong points of vector search. You finally get results where before no results were there, but maybe some of you have already spotted it when I showed you the slide with the gorgonzola cheese. Why is there a salami showing up? And the answer is, I cannot answer. The problem is, well, it's AI. It does magic, and the magic gives you some results, and first result, great. Second result, okay, cheese, maybe somewhere in the description, another cheese, but salami? And this is really the problem with, when using vector search. You can no longer explain to your customers why things show up in their search. Using traditional search with full text indexes, you really have a granularity in fine-tuning your search, where data comes from, which columns make up the result. But in this case, I simply cannot answer why you see a salami. So, yeah, that's bad. And one other problem with a vector search is, you might have also spotted that I limited the search results to the closest 10 things we found in our database. But closest 10 things in the database can still be very, very far off. I tested it with just using my fist and hitting the keyboards, and you got some random strings. And still the vector search gives you results. Nice. They have nothing to do with the thing you entered, but you get results. We talked with a customer about it, and they have an online shop, and their answer was basically, well, I got a search, and it's always better to show them something than nothing, and maybe they will figure out, oh, nice, I did not know they have Gorgonzola in their shop. Now I know I can order it. Well, as long as it sells more products, I think they are happy. But that's something you have to keep in mind with vector search. And the big question with this large downside of not really having control over it, I bet you can fine-tune it, but it's really, really hard to fine-tune. And as soon as you switch your embedding model, well, you basically start from zero. And the big question is it worth it to use with this uncertainty on how it really performs? Well, of course it is. But when we played around with it and we tested it, it became clearer to us that at least for now, our question for what search you should use, the answer is use some kind of hybrid search. We started to implement hybrid search, where you basically combine both your full text index and your vector search, and you can combine the strong points. In the ecosystem, we already tweaked the search over 3 years, combining different data and even searching for the name of the menu where the product is included and everything. And in those general searches, our search already performed really, really great, and we know how to improve it. But as soon as somebody mistypes or they try to describe what they are searching for, as soon as that happens, vector search and your full text index basically falls apart and cannot find anything. Well, hit up your vector search and you get a bunch of hopefully nice results. So the answer is use both. Thank you for coming and for listening to me.
Thank you, Alexander. I think this is the longest turnout of questions I have seen.
Oh no.
This is the last talk on this.
Is the microphone turned on?
No, I don't think so.
Okay.
I mean, yes, it is, but
okay.
Hello? Hello, thank you, wonderful.
Hi.
So let's spend a bit of time and go through them. Someone commented, Gorgonzola and salami both use Schimmel, which I guess makes sense. So I thought about that too, but I couldn't see the salami well, so
nice.
That works.
So there's one answer.
That could work. So how does the LLM stay consistent when creating embeddings? As in, like if you create 100 embeddings today and then 100 tomorrow, they need to kind of fit into the same vector space. Yeah. So do these embedding models do that naturally, or do you need to do something for that?
Well, when you're looking at the size of the vectors, they stay the same. but I would bet that they end up in different spots in the vector space.
Right.
But we've tested it with the Ökokisten, and the search results did not really differ from time to time, even when re-indexing and clearing the database and filling it up again. So it was really consistent, as long as you're using the same embedding model.
Of course, that makes sense.
Yeah.
Okay. Okay, so you mentioned how you use Mistral for that.
Yeah.
How does it work in practice? Like, what do you send to Mistral and what do you get back?
Okay, so we are using the batch API. There's a nice callback API from Mistral where you just send them an URL that they will call as soon as your calculations are done, and we send them a bunch of. Okay. Now I know where the question is heading. So we got this nice package called KissSearch, which is some search abstraction layer for your NEOS content, and that already comes with the text extraction from your node types and all of your data, and the process of linking the contents back to your documents. KissSearch already comes with that, and there's an API point to jump into this the indexing process of KissSearch. So basically, the process of creating the content you want to index was already done, and then for each content we just go send them to Mistral, and Mistral responds with the embedding.
Maybe interesting at that point. Could you combine local models with as a fallback? Like if you run Mistral locally and the provided one, would that be compatible? Have you tried it?
I have not tried it, and I don't know if the local embedding model of Mistral is the same as the host.
Okay.
But given those are the same models, they would work together.
Okay, cool. Can you say something about API costs in production?
We indexed our product database with, I think, 5,000 products with description and everything, and re-indexing was like cents, points of cents, and running search queries is also really, really cheap. We have built some kind of cache, so especially when you got a web shop, you expect often search terms to be used and used and used again and again and again. So you can cache them and you can reuse them. You have to flush them as soon as the model changes. But to be honest, we have not rolled it out in full production mode yet. So I expect it to be like a couple of cents per month, but it really depends.
Sounds fair. In regards to full documents, like longer text, how do you retain context when creating the embeddings to find the right thing in the end?
The best thing is to have your NEOS documents to be really split up in different sections and different entries in text blocks. So basically, each block, you have to do it when you're editing the content. So when you're having one context, one thought, one thing, you have to have a good search. You have to put it in different text blocks. And then the embedding process only processes this context, and the vector search then will find that single that content node, and we would then link the content back to the document it was on.
Right. There's a couple of comments regarding additional topics. I think we can summarize that this talk was specifically about vector search, but there's a comment about prioritization, obviously, in the search results, which could be added on top, I guess, and also limiting the distance in the query to get less results with weird queries.
Yeah, I tried it, and especially we tried it on our Sandstorm website. And the problem I ran into it's really, really hard to define a distance, because depending on what you're searching for, well, the distance can naturally be in a certain range. I tried to play around with some thresholds, but it did not really work yet. But maybe I will somewhere find a fix for that.
In your experience from what you implemented so far, do you feel that exact matches also are represented correctly in the results?
They tend to have a really strong score or a really close distance to each other, but they are not as good as you would like search for exact matches using traditional search or like a full text index. So that's the reason I recommend to keep your full text index search still in your project, because there the full text index simply performs better.
Right. And finally, obviously you started with the Frischkäse.
Yeah.
Does it work now?
Yes, it does work.
Fantastic. Great. So no Käse mehr if you search for Käse.
Yes, you can finally get your cheese.
Thank you.
Thank you very much. Thank you soon.